In this video, we are going to talk about how arrays are stored as references. We've already gone through this once before, and that was with objects, but it's worth doing it again. So, remember what a reference is. That's a memory address in a location in memory. And so, when you issue a statement like this declaring an array, right, what you get in memory is a picture that looks like this, right? You get a memory address, right, that's associated with the variable nums. It has an address, right, that the computer uses. And then inside that memory address is not the array 318, but it's the location or reference, right, to another memory address. And if you go to that memory address, right, then you'll find where the array is. Now that's an oversimplification, but it's good enough, right, to get the point across. All right, and so the issue with that, right, is that you have to be aware of that, and there's a couple of consequences for arrays, and they are essentially the same too as the consequences for objects. So number one is that when you change a copy of an array, it changes the original and vice versa, right? So if I have, let's take a look at this example. Changing array copy changes the original. All right, so when I do this example, I've got a couple of things going on. Here I create some just regular variables, both of type int a and b, and I change the copy, which is b in this case, to 7, and okay. So right here, I create the variable a, and I store a 3 in there. I make a copy. I store the variable b in there. Okay. And then I change b to 7 and print out the result. And you can see, okay, b is changed to 7. I change a to 2 and print them out. And here's the result I get. A is changed to 2. Okay, and you can see that works exactly kind of the way that you think it would work with no issues. But the thing is I'm going to do exactly the same thing with that I did here with these two int variables with two arrays, and you'll see, right, that the situation is not the same. So here I create an array called C, and here I make a copy of it, right? I just declare another array called D, and I say set it equal to C. Okay. All right, and I print those out, and you can see this is what I get right here. I get the same array, right, which makes sense. All right, and so next up, what I'm going to do is change the copy of the array, all right, to 99. I'm going to put 99 in the first spot, and I'm going to print those out again. So you can see in between here, this print statement on line 35 and this print statement on line 41, I did not touch the array C, but if you print on line 41, when I print those out, you can see it did change the first element of the array D to 99. That's as expected. What is unexpected, right, is that it also changed the first number of C, okay? So look, if you look right in between here, there is nowhere where I changed C. Next up, I changed C to have negative 1,000 in the last element of the array to negative 1,000, and you can see, and then I print out the arrays again. Right, and you can see it changed the last element of C to negative 1,000 like I asked, but it also changed, right, the last element of the array D to negative 1,000, which I didn't explicitly tell it to do. It changed the copy, okay? And so that's an issue, right? You can see arrays do not behave the same as the primitive types do, and that's because they're stored by reference, like we just mentioned. All right, so here I am just printing out the hash of the memory address of C and the hash of the memory address of D, and you can see I get identical results right here. They're exactly the same. and that's what's causing this issue. If I run it through in Canvas, Control Shift R, with A and B, the primitive types, right, I get different memory addresses because they are stored by value. It just puts the value 3 in there, and it puts the value of B in here. So when I change B to 7, it doesn't affect A. When I change A to 2, it doesn't affect B, right? But when I try to do the same thing, right, with C and with D, they are stored as references, right? And you can even see that in the way Canvas displays it with this little arrow, right, coming out of here, as opposed to the way it displays primitive types. All right, and you're going to see I am going to print those out. I'm going to get the same value. I'm going to change D, right, to have a 99 in the first position at index 0. You can see it also changes C. I'm going to change C, and also changes D as well, right? And then I print out the memory addresses, and that's key here, right? They're stored as the same reference. So if you go back to the slides right here and look, right, when I created C, right, it set up the variable C. And remember, these arrays get stored as references, right? So it just stores the memory address here. And if you go to that memory address, you'll find the array, right, 479. Then when I did this line, right, when I copied C over to D, all it did was copy this reference. It created a new variable D, right, at a different place, but it copied this value over here. It did not make a copy of the array. So they are basically linked if you do this, right? And that's why really inside the memory, there's only one copy of that array, even though to you it looks like there's different ones, right? Because you're just basically going on the experience that you have with primitive values. So when you change this array, it also appears to change it for the array D. There's really not two copies in there. There's really just one, okay? And they just have the same reference. You can use that behavior to your advantage if you want to, but in other cases you don't want to do that, all right? If you want to prevent that type of situation from happening, you need to do what's called make a deep copy of the array. A deep copy of an array is another array with the same elements but with a different reference. Okay, and so that you have to be a little bit careful about that, right? Because if the array elements are stored as references as well, right, then you've got to make deep copies of those array elements as well. So we probably will not get into that situation, but I'll show you how to make deep copies a couple of ways. So let's take a look at the deep copy example. So in the deep copy example, I do pretty much exactly the same thing that I did in the previous, right? I create in the previous example, I create an array called C that has 479. All right, and then here is where the deep copying, or one way to deep copy, happens. So I create a new array called D, okay? And then what I do is I use a for loop to copy over the elements of C one at a time over to D. All right, so I'm really not copying the array. I'm copying the ints that are in the array over one at a time. And since they are primitive types, right, then it will copy just the values over, okay? So that's what this note up here, you have to be a little bit careful about that, because if we had arrays of reference types, then that's not going to work, okay? Because we would still, the elements in there would still be linked, okay? So there's other ways that we would have to deal with that. But, okay, so let's say I have this deep copy set up, and I'm going to run this. And then I'm going to do exactly the same things that I did with the arrays in the previous example, where I just made what's called a shallow copy, right? I'm going to change the first value. So here you can see C and D after I have them set up, making the deep copy. Here I am going to change the first element of D to 99 and then print out the results. And you can see that that did not affect C because I did a deep copy. All right. In the previous example, I changed the last value of C to negative 1000, right? And that also, right, affected D because it was a shallow copy. But here you can see after making that deep copy, then D is unaffected. Okay. All right, and you can see why here. If I take a look and here I print out the hash of the memory addresses again, you can see that they have different memory addresses, or at least the hash, right, is different. So is what you can see. So anyway, that's the situation with that. There is another way to make a deep copy here, and let me show you that. So in order to do that, I am going to comment out all of this. All right, and so line 25 here shows another way to make a deep copy. Again, this is assuming that the elements of your array are reference types. This will not work, okay, if the elements of your array are reference types. So here I create an array, C, and here I use the copy of method in the arrays class to make a copy of another array. So I put the array that I want to copy and then the length that I want to make it. And so here I'm copying the entire array C over to D. Okay. All right, and we're going to run it again, and you'll see exactly the same results. So after I make the deep copy using the copy of method in the arrays class, I print out C and D. You can see they're exactly the same. I change the first element of D to 99. You can see that C is unaffected by that change. And then I change the last element of C to negative 1000. You can see because we made a deep copy, right, then D is unaffected by that. And again, when I print out the memory addresses or the hash of the memory addresses, right, you can see that they're different. So these things are stored at different locations in the memory. All right, and so what this would look like sort of in pictures would be a situation that looks like this. After you make the deep copy, right, then there is actually another copy of that array in memory. It's stored at a different location than the copy for C is stored, right? So you can compare those two situations. When you just copy it over like this, what's called a shallow copy, right, it just doesn't really make an extra copy. When you make a deep copy, right, it looks like this, and so changes that you make to this array will not affect the other one, and vice versa. Okay, so that's a deep copy. All right, the second consequence of arrays being stored as references, just like with objects, is if you pass an array to a method, right, as a parameter, and then change the parameter inside of the method, even though it's called something different, right, what it does is it changes the original and vice versa. Just like before, in some cases this is beneficial, in other cases it's not, right? We have seen, if you watch the array about, or the video about sorting arrays, in there, this technique, the fact that this happens, is used to be able to sort the array in place like that. In that sort method, it takes advantage of the fact that what I'm about to show you happens, and so it makes the syntax of it slightly easier. Okay, but again, other times you don't want that to happen. So let's take a look at the example. All right, so in this example, oops, nope, that's not the right one. It's passing arrays to methods. Okay. So I make a I do this twice. Okay, so first I create a variable of primitive type and I pass that to a method. All right, that method is method A. I change, so that value of A is going to be stored in this parameter val. Okay, and then inside that method I change val to 7. All right, and then that method gets done. And then I'm going to print out A, and you'll see that A is unchanged. All right, so let's run that and take a look at it. All right, so I create this variable A. I pass it to this method here. I change the value of the parameter inside the method. And the method ends, right? And so it goes back here, and I print out A, and A is still going to be 3. All right. So the reason why that's so, right, is because of the way primitive types are passed through methods. It just gives it the actual value, and so it's stored in a different variable. It doesn't change anything. Let's take a look at it in Canvas. Okay, so here I set up that variable A so you can see it. Here I call the method A. All right, that sets up this variable here, right? That's the parameter val, and so the value for A got sent over here. Inside the method, on this line 35, I change the value of the variable val to 7, and you can see that does not affect, right, the variable A. The method is over. So it bumps back to where it was called from, right here, line 11, and continues to line 14. And if I print out A, it's 3. No problems whatsoever. Okay. All right, we're going to continue. Here, now I create, and this behavior, like you just saw, is exactly the kind of behavior you think it should have, right? So that nobody is surprised about the results there. All right, so now what I'm going to do is create an array B. All right, and then I am going to call method B, and I'm going to send this array to that method, to method B. All right, so method B is down here, and you can see that method B has one parameter, right, named val. All right, and I'm going to drag that over, and you're going to see, right, that that value, the value of this array B, was sent over here. But really, it's not the value that was sent. Okay, what was really sent was the memory address where where array B was stored. Okay, so that's the issue. When we did it with primitive types, it just sent over the number 3. Here it sends over the memory address where it's stored, and that's what's going to cause the issues. Okay. All right, so inside this method, method B, I am going to change on this next line, right? I changed the first element of the array val to 7, and you're going to see that unlike the previous situation, it is also going to change the value for B, which is back up here. Okay, so here we go. And you can see that exactly happened, right? It did change the value of the first element of val to 7 as expected. What is maybe not expected, right, if you're not aware of references and how they work, is that the value of B changed as well, right? And so now the method is about to be over, right? So the method B is done. We go back, right, to where it was called from, which is line 22. And you can see, right, it changed the value of B. So if you're not aware of that, right, inside here, if you look at the code, there's no reason to think at first that B would be changed, but sure enough, it does get changed, okay? And that's because it didn't actually pass it a copy of val. It only passed the memory, or it did not pass the actual values, right, to the method. It only passed the reference. All right, so if we look back here, we can see this situation. Right here, this should say B, right? As B is the variable that I used for the array here. All right, so I set up B. So again, this should be B right here. And that's going to store in the variable B is going to be the reference or the memory address, right, where this array is stored over here. And then I called that method B. Method B has an array parameter. You can see, right, the brackets there, letting you know that this is an array. But it did not send 4, 7, and 9 down there. What it sent was actually this reference right here. So it's kind of lazy. It says, I'm not going to copy all this stuff. I'm just going to send you this memory address, and then you can go find what you're looking for over there. So the value of val, right, had this same memory address. It didn't really make an extra copy of that, okay? They're linked. And so whenever you change val inside the method, right, it is going to change the original B as well there, okay? All right, so that's the situation with arrays and being stored as references. All right, if you want to avoid that situation, then what you will need to do is to make a deep copy of the array or object before passing it to a method. All right, that's it for this video.